everything you need to know about physics collisions. Okay, not everything, but come on. So let me go over the very, very important things about collisions. I'm going to start mostly in one dimension, and then I will get to two dimensions. This will be aimed at the algebra-based physics level. A lot of this still applies to calculus-based physics, and even high school stuff. So, but that's where I'm at. I'm going to show you why momentum is conserved, and then I'm going to use that to show you how an elastic, inelastic, plane collisions, what does a plane collision even mean? You will find out. And then two-dimensional collisions with Python. So it's going to be super epic. Let's just start with a fresh sheet of paper, and let's imagine that we have two colliding objects. So here I have object A, and here I have object B. And they can be in 2 dimensions, in 3 dimensions, in 1 dimension, doesn't really matter. And so object A is moving with the velocity, I'll call it VA1, and object B is moving with the velocity VB1. And then they collide. So let's say they're right here, they're in contact, and then afterwards A goes off like this, and it even changed size, see, it got smaller, and then B goes off like this. This is A, B, and then B goes off like this. So we actually don't want to look at the velocity. I drew the velocity as a little introduction, but we want to really consider momentum and the momentum principle. So we define momentum as P equals mv. So it's the product of an object's mass and its velocity. So really we want PA1 and PB1. And then after the collision, we'll call this PA2. So the 2 means afterwards. And this is PB2. So those are momentum vectors before and after the collisions. This also goes along with the momentum principle. So if I define that as momentum and you want to start with Newton's second law, which I get it, everyone does that. Let's start with Newton's second law that says F net is ma. You've seen that. But A is defined as delta V over delta t. This says that if the acceleration is constant, it's a change in velocity with respect to time, and velocity is a vector. So if I put that in right here, I have F net equals m delta V delta t. But if the mass is constant, I can actually bring it into this change, and I can write this as delta mv delta t. And that mv is momentum. So we get delta P over delta T. So this is a different way of thinking about Newton's second law. And I kind of like it better, and I wish textbooks would start with this, and some do, very few. It says the following. It says, what do forces do? Forces change the momentum of an object. And I think that's a little bit better than saying mass and acceleration. You can get there the same way, and there's only a few cases that this doesn't work. I'll go ahead and tell you the 2 of the cases. One is if the mass is not constant, this doesn't really work. Which is a kind of a weird situation, but let's just say that. The other one where this actually does work, and you could take the derivative. This could turn into a derivative as delta t goes to 0. The other place that this is better is if you have particles moving near the speed of light. There's a different expression for momentum, and this still works. Okay. So if we use the momentum principle up here, let's look at A. A is coming down here. It collides with B, and then it has some new momentum. And if this is in space, there's only one force acting on A, and it's going to be this force FB pushing on A. So if I write the momentum principle, I have FB on A is going to be the change in momentum, which is going to be equal. Let's just write that as delta PA. The change in momentum of A with respect to time. I can do the same thing for B. It has one force acting on it, FA pushing on B. And notice that FAB is equal to negative FBA. Why? Because they're the same force. Forces come in pairs. Forces are an interaction between those two things, two objects. So if A pushes on B, B pushes on A with the same magnitude of force but in the opposite direction. That's that Newton's third law. Forces come in pairs. So I can write that for the other one, F A on B equals delta P B delta T. Let's solve this for delta PA. Delta PA is FBA, I'll leave off the arrow, delta T, and delta PB is equal to FAB delta T. But if the collision for B takes the same time as the collision for A, and why wouldn't it? How could A be in contact with B for a different time that B is in contact with A? Then the delta T's are the same, and these are opposite values, so I get delta PA equals negative delta PB. Because this is negative of that. And that's our conservation momentum. And it doesn't look like conservation momentum. That's fine. I get that. We can rewrite that if you'd like. Let's write it in terms of this. So I said delta PA equals negative delta PB. If I add that to both sides, I get delta PA plus delta PB equals 0 vector. And that is the vector because that you can't have a scalar on the other side. Now let's write this as PA2 minus PA1. That's the change in momentum. The final momentum minus the initial momentum. Do the same thing for B. Plus PB2 minus PB1 equals 0. Now what I can do is add PA1 to both sides, add PB1 to both sides. I get PA2 plus PB2 equals PA1 plus PB1. So this is the momentum before, and this is momentum after. So a lot of times you'll see this as P total 1 equals P, that's actually 2, but the same thing. P total 2. The total momentum is the same. So we call this conservation momentum. Conservation. You have to sound it out as you write it or you'll make a mistake. Momentum. Conservation momentum. Now, there is something special about this. We say that momentum is conserved in this collision. But when is that true and when is that not true? So, what made this whole thing happen was this. If the total force on A is the exact opposite of the total force on B, then momentum is conserved for the same time. But imagine if I have like a rocket on this one. Now I have an extra force over here. The change momentum of A is not going to be the opposite of the change in momentum of B. Okay, so as long as there's no external forces, momentum is conserved. So this is true. No external forces. Now we can cheat. So if I have two things that both have a gravitational force acting on them, but the collision time is very short, if delta T is very short, then this is approximately true because they'll both have an extra force added in them. But since delta T is very small, we can ignore that extra force. If the collision force is much larger, we can ignore it. So if you have two balls and you toss them in the air and they collide in the air, if you look at the momentum right before they collide, the momentum right after they collide, then they should be have equal momentums. Okay, now let's look at a special case. We're going to start in one dimension. I told you that we were going to do this. This is an elastic collision. A lot of people start with inelastic collisions, and I respect that, okay, because the inelastic collision is a lot easier. But in terms of Python, that's not true. So let's look at an elastic collision in one dimension. So suppose I have a car right here, M1, with an initial velocity in the x direction. So this is a scalar. I'm going to call it v1. And then I have another mass over here, v2, m2. And actually, this is va1 equals 0. vb1. No, this one's 0.5. And let's say m1 equals 0.25 kilograms. And let's say M2 is 0.25 kilograms, same thing. They collide, and what happens is, in this case, they will have M1 with some velocity VA2 and M2, and that's not actually what's going to happen, but that's fine, with some velocity VB2. Now, an elastic collision happens when there is, it's a very springy collision. Think of a very bouncy collision. It's actually a special case. In this elastic collision, we have the following. P total 1 equals P total 2. We knew that. This is true if the only forces acting on these two cars is the internal force of the two interacting with each other. Now imagine these are on a track. There's a downward gravitational force, but that's balanced by an upwards normal force. So those two forces don't change in momentum because they cancel. And so this isn't too terrible of a situation as if there's no friction. That's true for this collision with only internal forces. But an elastic collision says something else. K total 1, K total 2. So the kinetic energy before and after the collision is also the same. So if I come up here and say 1/2 M1 VA1 squared plus 1/2 M2 VB1 squared, that would be equal to 1/2 M1 VA2 squared plus 1/2 M2 V2 squared. So I'm going to go ahead and solve this situation for this very simple case. Let's use these two equations. Momentum is conserved, kinetic energy is conserved for the case where this starts at rest and they have the same mass. That's an easy one. Other than that, it can get a little complicated. So I'm going to solve that one just as an example, just to get it started, and then we'll look at a Python model of that. So here I have M1 V1, and this is M2, which is the same thing. We can just both call those M, and this is 0. And then after the collision, I call that VA1, I'm sorry. Then after the collision, they both have mass M, and that's VA2, and this one is M VB2. So let's set up the conservation momentum equation in the x direction, because they're only moving in the x. So I have the total momentum before is going to be M1 VA1. I'm going to drop that 1. It's just going to call it M plus 0. And that's going to be equal to M VA2 plus M VB2. Now, in this equation, I know the initial velocity. Let's say this is VA1 equals 0.5. And let's say M equals 0.25 kilograms. So I know that, but I don't know either the final two velocities. I just know that the momentums of these have to add up to that. I can go ahead and do some little algebraic manipulation. Since they have the same mass, I can divide both sides by that mass, and I get VA1 equals VA2 plus VB2. So that's one equation. Now I need two equations to solve for two unknowns. I don't know that either of those two things. So let's do the kinetic energy equation. So the kinetic energy before is going to be 1/2 M VA1 squared plus 0, because that one's at rest. And that's going to be equal to 1/2 M VA2 squared plus 1/2 M VB2 squared. Okay, so I can multiply both sides by 2 and divide by M. I get VA1 squared equals VA2 squared plus VB2 squared. So I have two equations, two unknowns. Now, there's a couple ways to solve this equation. But let's just guess at a solution, because I don't want to get into the algebra of this. I want to focus on the collision itself. Let's just say VA1 equals 0.5. So here, what are some options? Well, each of these could have the same velocity, 0.25 and 0.25. Or let's say this is 1. let's say it's 2. VA2 equals 2 meters per second. So then this could be 1 and 1. But if that's the case, over here I'd have the initial velocity squared, which is 4. 1 squared plus 1 squared is not 4. So it doesn't work. Okay. Really, if you play around with it, there's only one number that you can add together and get a number, and square them and add them to get the same number, and that's 1 and 0, or 2 and 0. Okay. So one of these has to be 2 and one has to be 0. That's the only way this will work. And that's the solution. So if this car comes in and collides, it's either going to miss so that one stays at rest and it passes through, or this one's going to hit and stop and that one's going to move off at the same velocity. Okay, let's model this in Python. I got it all set up and I've already written this program. I'll show you the program and I'll explain it to you, but we can check if the kinetic energy is conserved and if the momentum is conserved. The way I'm going to do this program is to have two masses in Python, and I'm going to have a spring connecting them. And so if these two masses get within a certain distance, I'll call it L0, then there will be a spring force pushing them apart. And once they get further away than that, then there's no force. So this is just like a real car. They come in contact, there's a force of this car pushing on that car and this one pushing on that one. And then I can use that to update the momentum over a short time and repeat that multiple times. So this is your classic numerical calculation. If you haven't seen this before, let me know. I have a good tutorial on numerical calculations. And I'm going to give you the code. This code's online. Okay, so let's just jump over here and look at this perfectly elastic collision in Python. Okay, so here's the code. Let me just run you through it real quick. All this stuff up here, this just makes a graph. I'm making a bunch of graphs. I'm going to graph the momentum as a function of time in the x direction, the velocity in the x direction, the kinetic energy. So here I have car 1 is 0.25 kilograms. Car 2, let's put that at the same thing. Car 1 is just a box. That's all. Car 2, I made the box so that the mass, the size is proportional to the mass. Then car 1 is moving at 0.5 meters per second. Car 2 has an initial velocity of 0. I set up their initial momentum vectors. This is the spring constant between them. And so I was trying to get really nice graphs. So my spring constant is super high, but that's fine. I have a super high spring constant and a super short time interval. So that's that. L is the length between the length of the springs, and this is the distance between the cars, the centers of the car plus the spring. Let's see if it's raining. Okay, and then time step. This is the force of one car pushing on the other. And I set it to 0. And then what I do is I check, are they within that pushing distance? If that's the case, then I set that equal to some spring force pushing them apart. That's just printing. Oh, collide equals false. That's for something else. Calculate the kinetic energy right here. And then here I calculate the distance between them. I check and see if there is a force. And if so, I calculate it. I use that to update the momentum of each car. I use the momentum to update the position. And then that's it. Okay, so let's run this and see what happens. There's your one car, and it looks like it bounces back, but it doesn't. It actually stopped. The camera zoomed out, so that's why it looks like it does that. If I look over here, here is my momentum graph. So you'll notice that before the collision, the car 1 had a momentum of 0.13, and the other car was at rest. And then here's during the collision, that part right there, and one stops, goes down, and the other one starts up, and the total momentum, this dotted line, is constant. And that's exactly what I'd expect. Here's the velocity graph, very boring. Same thing, because they have the same mass. And then here is the kinetic energy graph, right? So the kinetic energy before is something that's 0, and they just swap. So let's go ahead and change this so that the second car is more massive. Where to put my mass? Let's say it's 1.5 times the mass. Now that solution that we use won't work. But what we really want to see is momentum conserved, is kinetic energy conserved? So you'll notice that one did bounce back. And here's my momentum. Momentum, the green dot is straight, even though there's a collision. So car 2 gets kicked up to some speed, and car 1 bounces back. That's the momentum. Okay? That's the momentum. It's not going faster than the original car. It has more momentum because the other one has a negative momentum because it bounced back. If you look at the velocities, the velocity of the red car is not as fast as the blue car, but the blue car bounces back. And then if we look at the kinetic energy, that's conserved. Okay? So pretty happy. So that's your elastic collision. Perfectly elastic collision. Let's look at an inelastic collision, which is a little bit easier. Switching back to paper. Okay, so if I look at an inelastic collision, inelastic. So the key here is for an inelastic collision, I have car A coming in, and it collides with car B. And I'm starting car B at rest just because it's easy for right now. And then afterwards, what makes this unique is that the two cars stick together. So they have the same velocity afterwards. And that's fine. We still have momentum as conserved. Imagine that these two cars come and stick. There's some force pushing them apart and then pulling them together. So imagine like a decaying spring constant between them. Or spring, it's fine. So I still have P total 1 equals P total 2. Let's do the simple case of masses of the same thing. So here's V1 A1 equals 2, just like I had before. That's M, 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 M. So in this case, I don't need to solve for the kinetic energy because I only have one variable at the end. The momentum beforehand is going to be M VA1 plus 0. The momentum afterwards is going to be M VA2 plus M VB2. But VA2 equals VB2. They're stuck together. So let's just call it VA2. So now I have M VA1 equals M VA2 plus M VA2. And that's going to be equal to 2M VA2. If I solve for VA2, the mass cancels. I can divide by 2. VA2 is 1/2 VA1 in this case. So if that started off with a velocity of 2, this would be 1 meter per second. Let's just check the kinetic energy. So KE1 is going to be 1/2 M VA1 squared plus 0. KE2 is going to be 1/2 M VA2 squared plus 1/2 M VA2 squared. So let's just say the mass is 1 for right now. So I have, this is going to be 1/2 times 1 times 4. That's going to be 2 joules. Here I have 1/2 times 1 times 1 is going to be 1/2 plus 1/2 times 1 times 1. So that's going to be equal to, this is going to be 1/2, that's going to be 1/2, it's going to be 1 joule. So it has less kinetic energy after the collision. We lose kinetic energy in this collision. Okay? We don't lose energy. We lose kinetic energy. It is transformed into other forms, thermal, deformation energy, something like that. This one is actually not very easy to model because if I have that spring pushing them apart, I want to actually, once they collide, after they collide, have that spring kind of stick together so that it does not let go. So if they move further apart, it pulls them back. It doesn't just push them away, it pulls them together. And if I do that, what will happen is they'll collide together. So if I have this car coming in, it'll collide, and then they'll just shake like that. And it looks a little bit bad. So what I'm going to do is actually add a drag force. I'm going to say F drag is negative C P A1. That's going to be the drag force on that one. And then if I add a force to that, that's fine. As long as I add the opposite force to this one, then the total internal, then those two forces are an internal force and they won't change the momentum. Okay. As long as I do the opposite of these two things, as long as the forces acting on these are an equal and opposite, that's fine. So I can do that. And that's what I'm going to do. So let me show you how that code works. jumping over back to the computer. Okay, so I got all these pulled up. Where'd it go? There it is. The code looks the same. It's mostly the same. What's different? Let's put this back at 1. I have 0.5. The other one starts at rest. KL collide. Over here I have this collide equals false. Okay, so that's important because I need to know once they do collide, then I can say don't let go of that spring. Keep that spring force acting. This C right here, that's that drag coefficient for the momentum, which is totally made up and unrealistic, but I just want it to look good. And as long as I have the same force in the two, that's fine. I can cheat. Cheating is okay, as long as you do it within the bounds of reason. So other than that, I say if the collision is false, if they have not collided, then every time I go through, set the force equal to 0, and that's fine. Again, calculate that distance between them. And then here is the collision force. Notice that I add that negative c times car 1 dot momentum. And that's fine because I calculate that force. Down here, car 1 has car 1p plus f delta t. The other one has minus. So they have opposite forces because I put a minus here. And then I calculate the momentum. I calculate the kinetic energy. Let's run this thing. There it comes. Boom. And you'll see here that in the momentum, the momentum is conserved. And now this oscillation down, that's because of that drag force. If I didn't have that, it'd just keep oscillating like brr, brr, brr. And so that I kind of like it, but it comes down here to half of the initial momentum, which is for each one though. See, this one speeds up and that one slows down. So the total momentum is still constant. The velocity graph looks the same because they have the same mass. And then the kinetic energy term, notice this. Yes, the momentum's decreased, but since the velocity is squared, those velocities don't add up to the same thing. And so I have less kinetic energy than what I have. Kinetic energy is not conserved. There is kinetic energy, and we can find that change in kinetic energy. It's just not constant throughout the thing. If you take into account the energy loss due to the drag force and the spring elastic energy, energy is conserved. All right, let's change this one. Let's put a larger mass, 1.5. My code's very sloppy, I admit. I'm a sloppy coder. Okay, so now it's bigger. You can see that. They're going to stick together still. And over here, they don't have the same final momentum. But those two momentums add up to the same constant. So the momentum is the same. And then the velocities are the same because they're stuck together. That's what we said. And the kinetic energy is not constant. Okay, now what about what I call a plane collision? Let me get to my paper. A plane collision. A plane collision in some ways is the hardest because a plane collision, I got to write it out first. Oh, what happened? There we go. Okay, plane collision. This would be a collision between two masses. And again, I'm starting with the same m, and this one's moving some velocity v. They collide, and then they're both moving afterwards. But kinetic energy, not constant, not conserved. And VA2 not equal to VB2. So it's not elastic, it's not inelastic, it's somewhere in between. They just collide. They just collide and they have masses and velocities afterwards. So if I write the conservation of momentum equation, it should still work. I can still say mVA1 plus 0 equals mVA2 plus mVB2. But I don't have a kinetic energy equation. I have two variables I don't know. I don't know this and I don't know that. So the only way you can solve this is if you know one of the final velocities. One final velocity known. Otherwise, you just can't do it. But if you do that, then you can do that and you can solve for the kinetic energy. Now, how do you model this in Python? That's actually very difficult because what I want to do is I want them to collide and I want a spring to push them apart. But what I'm going to do is to prevent them from conserving kinetic energy, I'm going to have a variable spring constant. So when they collide, so if they're moving towards each other, relative, then I'm going to have a stiff spring. But once they move apart from each other, I'm going to have a weak spring. So if I change the spring constant depending on whether they're moving towards or away from each other, then what the work done, the energy stored in the spring will not be the same for compressing and uncompressing, and so I lose some energy. So momentum will still be conserved as long as this force acts equal and opposite on the two masses. That's all I need. Okay, so it's a lot like the elastic collision calculation. The only difference is that I need to check if they're moving towards each other or away from each other. So let's go ahead and look at this code. I call it a plane collision. So again, the code is pretty much the same. That's all the same. Let's put this at 1. Okay. Here I have two spring constants. So I have K is 6,000, and then I have K2 is 2,000. So that's just the spring constant once they're moving apart. Now the other thing down here is I have this. R old. R old is the position relative to the distance between the centers. Okay. And I'm going to change that. And so in order to change that, I need to check what it was in the past, because I need to say, is R getting closer or further apart? So I need to start with an R old. At the end of every loop, I'll reset R old. And you'll notice that this is set in the X directions. I've restricted it to the X direction because if I make my mass larger, its center is up here, and you would get like a two-dimensional collision, which we're going to do in just a second. So down here, I say if they're colliding. That's what that says. This says if R is less than R old would mean they're moving towards each other. And so I'm going to use K. Otherwise, then they must be moving away from each other. So I'm going to use K2. So I just change those two equations. That's it. One of these equations has K, one has K2. And then I say collide is true, so which I don't think I need that. Well, it works. Okay, then down here, right here, R old equals R. So what I do is I make the R old, what it was, I move R to the now called R old. When I get back to the top, I can compare it again. I can't keep R old the same. It's always the previous position. Let's run this thing. Here it comes. Boom. Okay, so it collided. Was momentum conserved? It should be if they have the equal and opposite forces. Was kinetic energy conserved? It shouldn't be, but let's just see. So here's momentum. That's a plus. It's conserved, right? Here's the velocity. No one cares about velocity. Kinetic energy, not conserved. They didn't stick together, and kinetic energy was not conserved. Okay, and then we could change those up. You can, if you want to, once you get this code, you can change the mass. You can give the other car some velocity. You can do whatever you want. You can do whatever you want. I don't know if you can, but. So now you see that cart's a little thicker. If I use the height of that as a center, then they're not both in the X direction. Okay, again, kinetic energy not conserved. Okay, we have one more collision. I'm not going to show you this fully, but this is one that is pretty cool. Let me switch back to the overhead. This is a two-dimensional collision. Now, this can get a little bit complicated, especially for a two-dimensional elastic collision. But imagine that I have a ball here and a ball there moving this way, like that. And now when they collide, you'll notice that since they're not in a line, if there's a spring connecting them, that's going to push that way and that way. So this is going to be the change in momentum in this direction. This is going to change momentum in that direction. So they will actually move off like that. So if I know these angles, theta, let's call this theta A and theta B, I can still do conservation momentum. I can still say P total 1 equals P total 2. But that's a vector equation. And so when I deal with vectors, one thing that we can do is to break this into an x and y direction. So let's call that x, y. So here I will say, if I have it just like this, I'm going to say mva1 plus 0. Because if this is moving in the x direction, then it has only x component in the x direction. After the collision, I have mva2, but I want just the x component of the velocity. So here's my velocity. That's my x component. That's my y. That's my angle theta A. So I'm going to say cosine theta A. And then this one also has an x component of velocity, mvb2 cosine theta B. So that's my conservation momentum equation in the x direction. Now I can do the same thing in the y direction. So this one has 0 momentum in the y direction before the collision. Afterwards, here's a little trick part. I'm going to have mva2 sine theta A, right, because that's the sine of the angle, minus mvb2 sine theta B. Why is it minus? Because this has a velocity in the negative y direction. So it depends on how you measure that angle, but I know that's moving in the negative y direction. I better darn well sure make sure it has a negative velocity, negative component of momentum. Okay, so now I have two equations, but you could have, depending on what they give you, if you know these angles, then you can solve. Okay, if you don't know those angles, then you're going to be in trouble. If you don't know those angles, there's a way to do it, but it gets complicated if it's an elastic collision. Now, is kinetic energy conserved? Well, in that case, it'd be 1/2 mva1 squared equals 1/2 mva2 squared plus 1/2 mvb2 squared. So that deals with the magnitude of the velocity, so you can't break that into components. Modeling this in Python is actually very easy because I've already done all the work. All I have to do is change these to spheres instead of boxes. And if I take this as A, which in the program I call them 1 and 2 because I'm dumb, and then I find this vector R is going to be RA minus RB, then I can say, is that vector less than the sum of their radiuses? If so, there's a force pushing them apart, and I can use that vector R to find this force very easily. Other than that, it's the same code. Let me show you. Back to the computer. And 2D, this is actually a 2D plane collision. Where's my mouse? 2D plane collision. I think it's a 2D collision. Okay, so what do I have here? Notice that car 1 and car 2 are spheres now. They're not boxes. And I start this one a little bit in the y direction because I want it to move towards each other and have a glancing collision. Otherwise, you don't get that whole thing to work. I calculate R. Oh, this is an inelastic two-dimensional collision, which is easy to do. All I have to do is change those to spheres and put them in 2 dimensions, and it works. So let's run this. That's all I did. Here comes the ball. It collides, and it bounces, and then they have trails too, because no point in leaving trails in 1 dimension. So this is the x component of the momentum. So the x momentum is conserved. I can change this to the y component, which I'm going to do in just a second. But momentum is conserved, so that's good. The velocity isn't that useful, and then the kinetic energy is not conserved. Okay, we can change that. So let's go up here and look at the y momentum. So this would be changes to y, y, and y. And now you'll notice that the total momentum before the collision, 0. One car has a positive y velocity, one has a negative y velocity, but the total is still 0. What if I want to make it An elastic collision, I can do that. This is like a great program. It has everything in here. If I change this to 6,000 and I change C to 0 and say times 0, now it's an elastic collision. Let's see if the kinetic energy is indeed conserved. And down, look at that. Kinetic energy conserved. Okay, so that was a little bit longer, 40-minute long video. I don't know if you made it all the way to the end, but if you did, I'm going to remind you that I have the links to these two codes down below if you have any questions. All you have to do is say in a comment, hey, I don't understand why you did that, and you type it, and I'll probably reply. So there's a good chance I will. And I have more videos on this stuff. If you have questions about the code, I'll be happy to help. But that's that. I'll talk to you guys later.